Welcome back to another episode of the LLM Chronicles, where I, Donato, walk you through large language models one sketch at a time. In this episode, we're going to take a look at how neural networks function, covering artificial neurons and how they're stacked together to create multi-layer perceptrons, how to model inputs and outputs so that our network can process them, and then we'll close by looking at vectorization, which is used to implement neural networks efficiently on specialized hardware such as GPUs. So, what exactly is a neural network? It is a computational model inspired by the human brain. Just as the brain's computational power comes from its billions of interconnected neurons, neural networks draw their strength from connections between simpler units called perceptrons. Perceptrons are the cornerstone of every neural network. Proposed by Frank Rosenblatt as far back as the late 50s, a perceptron mimics the fundamental behavior of a biological neuron. Think of it as a node that receives various inputs through its virtual dendrites. Each input is a number and comes with associated weights. These weights can be positive, negative, or even zero. They determine the influence of each input on the perceptron's output. Additionally, each perceptron also has a bias term. The bias allows the perceptron to have flexibility, enabling it to fit data better. The perceptron takes these weighted inputs and sums them up, adding the bias value. Then the result is put through an activation function. In the original 50s model by Rosenblatt, the activation simply returned 1 if the sum crossed a certain threshold. You can think of it as the perceptron firing or activating. The activation function can be anything really, and it's often used to introduce non-linearity when connecting multiple perceptrons together, which is essential to increase their computational capabilities, as we'll see shortly. Historically, the most popular activation function was the sigmoid function. The overall shape goes smoothly from 0 for large negative values to 1 for large positive values. Another popular activation function is the tanh, which is just a shifted and scaled version of the sigmoid, so it goes from -1 to 1. The rectified linear unit, or the ReLU, is also very popular. The output equals the input when the input is positive. When the input is negative, the output is 0. Individual perceptrons are quite weak computational elements taken on their own, and they can't actually model very complex functions. But our brain is not just made of one neuron, it is actually a network of many neurons interconnected together. And we can do the same with our computational models. We can take the individual perceptrons and link them together in more complex structures. When you link several perceptrons together into layers and stack these layers, you get a multi-layer perceptron, or MLP. The first layer is the input layer. This layer does not contain perceptrons or neurons, it is more like a distribution layer that feeds the actual input data into the network. Each node in the input layer corresponds to a single feature in the input data, as we'll see later, and it directly passes its value to the next layer. Then come the actual perceptrons in the hidden layer. These are typically implemented as fully connected layers. That is, each value of the input layer is connected to each perceptron or unit in the hidden layer. Here we have a compact representation of a perceptron with its unique set of weights. Finally, the individual outputs of each perceptron in the hidden layer are fed into the perceptrons of the output layer. We'll see later how to set up this final layer for different tasks such as classification and regression. There can be many hidden layers, making the network arbitrarily deep. Different hidden layers usually have different numbers of perceptrons or units. The number of inputs in one layer is equal to the number of perceptrons in the previous layer. MLPs are feed-forward networks, which means that the computations, also called forward pass, are performed unidirectionally from input to output. The nonlinearity added by the activation functions that we saw before is critical when connecting perceptrons into MLPs. One way to look at this is that without a nonlinear activation function, a neural network will only be as powerful as just one single layer perceptron. It does not matter how many layers it has. But MLPs with nonlinear activation functions become universal function approximators. In simpler terms, this means that theoretically, you can create a neural network that can mimic any function you'd like, as long as that function is continuous and you have enough resources. So why is this capability of MLPs to approximate any function so useful? The answer lies in the vast range of applications it opens up. Since many real-world problems can be expressed as functions, the ability of an MLP to mimic those functions means that it can potentially solve or assist in solving those problems, whether it's recognizing your voice, translating languages, or even beating you at chess. Alright, so how can we use MLPs to model real-world problems? First, we have to transform the problem we want to model into a function that the MLP can compute. And the first step is to take the inputs and outputs of our problems and transform them into numbers. If we're dealing with something that's already numerical, this is straightforward. For example, a common approach is to reduce the complexity of real-world objects or phenomena into what are called features. Take the iris dataset, used commonly in machine learning. Each row represents a different iris flower, and the columns of features include numerical measurements like sepal length, sepal width, petal width, and so on. These values would form the inputs to our neural network. However, the versatility of MLPs means that almost any data can be translated into numbers. For example, sound can be converted into numerical amplitudes at specific time intervals. In this case, each feature corresponds to an amplitude at a given moment. Words within a text can be represented, for example, by their frequency of occurrence, making each feature the count of a particular word. When it comes to image recognition, such as identifying a cat in a photo, each feature can signify pixel information. In a grayscale image, this would mean each feature has a number representing a pixel's brightness. For color images, each pixel can be broken down into 3 numbers, the level of red, green, and blue, which together create any color visible on your computer screen. So now we can model any data into inputs for our MLP. But what about the outputs? First off, we need to define the task we want the model to perform. We might want our model to perform a classification task, that is, categorize input data into predefined classes or labels. For example, recognizing whether a picture contains a dog or not. This would be a binary classification task, predicting one of 2 classes, dog or not dog. For this, we set up our network with a single output node, whose value would be squished between 0 and 1 using, for example, a sigmoid activation. And this value will represent the probability that the input image represents a dog. If we had multiple classes, we'd set up the output layer of our network to have one output value per class. The raw output values of the last layer in this case are typically called logits, and then would be passed through a function such as the softmax activation, which takes a vector of raw scores and transforms them into probabilities that sum up to 1. So our network would return the probability of the input belonging to each of the classes. Another task we might want our model to perform is a regression, where the goal is to predict a continuous numerical output based on the input feature. Unlike a classification task, which aims to categorize inputs into discrete classes or labels, regression aims to map input data to a continuous output. Let's say we want to predict the price of a house based on its square footage. Now, we input the square footage into the network, and the output would be a continuous value representing the predicted price. Now, contrary to what you might expect, when we implement multi-layer perceptrons in the real world, we don't actually use data structures which mimic the visual representation of the perceptron, linking each input to each output manually. And the reason for this is that if we did so, it would be extremely inefficient. Imagine having to loop through each neuron, collect its outputs, and then pass those onto the next layer. That's a lot of loops and a lot of time. Instead, we use something called vectorization. In essence, each layer in an MLP can be represented as a matrix of weights. Each row of the matrix corresponds to the weights of one of the perceptrons in that layer, and the number of columns matches the number of inputs from the previous layer. The input data can also be turned into a vector. Now, you might recall the matrix multiplication operation you learned in your algebra classes. It turns out that when you perform a row by columns multiplication between this weight matrix and the input vector, you end up calculating the weighted sum for each neuron in that layer, all in one go. In deep learning, all of these vectors and matrices are called tensors. A tensor is simply a multi-dimensional array of numerical values, and it is used to generalize the concept of a matrix to an arbitrary number of dimensions. So it serves as the fundamental data structure for storing and manipulating complex data in neural network operations. And this is where GPUs come into play. Graphical processing units, or GPUs, are really good at parallel computing, which makes them ideal for this kind of tensor operations. They can perform multiple calculations simultaneously, speeding up the whole process significantly. Google has even developed TPUs, or tensor processing units, which are specialized for handling tensors in deep learning. Using vectorized operations also makes it very easy to work with batches of data. Instead of feeding the network one input at a time, you can feed it a whole batch. Just add a batch dimension to the input tensor and voila, the output of the matrix multiplication becomes a tensor with an additional dimension, each row corresponding to an item in the batch. So, there you have it. In this video, we've looked at perceptrons and how they can be stacked together to create multi-layer perceptrons and what the forward pass operation is like. In the next video, we will tackle the fundamental challenge of training such a network, which is learning a set of weights to perform a specific task. If you found this video interesting, be sure to hit the like button and subscribe to the channel. And if you've got any questions, just drop it in the comments below.